So we talked about SN1 and SN2 and the ways you can tell between the different kinds of nucleophilic substitution. Now we're going to talk about kind of the cousin or sister or whatever of SN1 and SN2. This is kind of related. It is elimination. So the basic idea of elimination is you have two carbons connected by a single bond, and they might have some hydrogens around them or something else, and you have some leaving group, which I'm going to say is X. And this is, by some mechanism, going to turn into this double bonded thing, and release this side product of HX. So how do we do this? Well, we had two mechanisms for substitution, SN1 and SN2. We have two related mechanisms for elimination called E1 and E2. And that 1 and 2 and E1 and E2 is also based on the rate law and what order the rate is. So E1s are first order and E2s are second order. And the reason why is because E2 happens all in one step, just like SN2, and E1 depends on that formation of a carbocation, just like SN1. And that formation of the carbocation is called a rate-limiting step because basically forming the carbocation takes so much energy and it's so much slower than the other step that the other step isn't going to determine how fast things go. So let's dive into it. We're going to start with E2. So this is E2. And we're going to have some substrate here with halogen on it, or whatever other leaving group. And I'm going to draw out the hydrogens that are here and the hydrogens that are here. The other carbons also have hydrogens, we're just not going to draw them out. Okay, and then we're going to have our base. And this base, or this nucleophile, it's going to have to be really big and kind of bulky, because what we're trying to do is we're trying to avoid doing SN2. And in order to do SN2, you have to get in here, right? So we want to create some steric hindrance. So a common one that you'll see is we'll take some kind of positive ion. Let's say we have like potassium, and we're going to have a tert butoxide. So these are all methyl groups on this carbon. So this carbon has got a lot of stuff going on, and if this tries to go in there, that's not going to work. So it's going to have to attack something that's kind of more on the outside. So it's got electrons, right? And it's going to act like a base, and it's going to attack one of these hydrogens over here. Now, why are we attacking hydrogens over here if our leaving group is all the way on that other carbon? Well, when you take an H as a base, you're taking a proton, an H+. So what's going to happen to those electrons? Well, those electrons are going to make the double bond. So these electrons are going to shift over here. And now all of a sudden, that carbon on the end, bound to the chlorine, has too many bonds, and it's got to kick something off. And it kicks off the chlorine. So in the end, we are going to have our product, which has, 1, 2, 3, 4, yeah, it's going to go like that. And we have K+, we have Cl-, and we have this tert butyl alcohol that got an H+ on it. So that is how E2 works, and generally the only way that we can tell if it's going to definitely be E2 and not SN2 is if we have this kind of steric hindrance. Otherwise, somebody's going to kind of have to tell us in the problem that we're solving. So that's E2. Now we're going to talk about E1. E1's going to be a bit more complicated because we have to make a carbocation, and I'm going to show you a special kind of E1 called dehydration. And this just means we're taking away an OH and we're taking away an H, and those are going to go off and be water. and we're going to have a double bond where they once were. So let's use this. And this can be acid catalyzed. That's how things generally work when we're trying to get rid of an OH in a first order reaction. In a second order, we had all those like weird things like a tosyl chloride or thionyl chloride or phosphorus tribromide. Here we just use an acid. So if we have H3O plus, this alcohol that we're trying to get water out of is going to act like a base, and it's going to take this proton and leave the electrons with water, or with whatever protonated thing that it might be. And so now we're going to have a nice leaving group here. And that leaving group is water. So that's where we got our water from. Now this is going to leave, take the electrons with it, and that's going to get us a carbocation. And now we can do the elimination part. So we have hydrogens here, right? And we have hydrogens here. And this water here is going to act like a base, and it's going to grab, that was a bad arrow, it's going to grab one of these hydrogens, and these electrons are going to make the double bond. And we can get a product. And we also regenerate our acid catalyst because we took the water and we protonated it, right? So everything worked out in the end. So you might have noticed something, that there's also hydrogens over here that we could have used, right? So in a different reaction, maybe the water took this hydrogen and it made this double bond. That is going to get us this kind of product. And you actually do get a little bit of that. And there's a reason that we get more of the first one that we drew. And the reason why is actually, it's kind of twofold. One of the things is that alkyl groups are going to donate electron density to a double bond, which is a good thing. So both of these guys are going to push in electrons, just like we saw with the carbocations and the plus I inductive effects. They're going to push in electrons toward this double bond and help it be stable. The other thing is bond angles. So if you have two groups that are on the same carbon, that's not the case here, but if you have two groups that are on the same carbon and you put a double bond there, you're increasing the bond angle and they're not as interfering with each other. So having a double bond where there's more carbons around it is a good thing. Or in other words, if it's more substituted, that's a good thing. And we're saying substituted because we're substituting hydrogens out and these carbon groups or alkyl groups in. So this product that we got originally, we call this, I'm going to erase the H3O plus, that's kind of misleading. Just this product with the double bond, we call the Zaitsev product. And that's after the guy who discovered this whole phenomenon. And this other guy named Hoffman also contributed in some ways, so we call this the Hoffman product. And the Zaitsev product, or the one that's more substituted, so when we're looking at substitution, we want to look at, here's the double bond, how many carbons are around it? 1, 2. And then on the other one, here's the double bond, how many carbons are around it? 1. Directly around it. I mean, so this one doesn't count. So the Zaitsev product is always going to be more prevalent, and the Hoffman product is not. And the way I remember these guys is Zaitsev is substituted and Hoffman is hydrogen, because there are more hydrogens on this one. There's 3 hydrogens here. Meanwhile, on this one, there's only 2 hydrogens. So that's what's going on when we get more than one product, is the Zaitsev product or the more substituted product is going to be favored. But some of both are going to be made. So that was dehydration in E1. How do we know if something is going to go E1 or SN1, right? Because we could have just substituted in, not the OH from water, that wouldn't matter, but if we had some other solvent, we could have substituted in instead of having it act like a base and make this double bond, right? Well, the main thing with SN1 versus E1 is heat. So if you see heat, that means elimination. So that's the way to tell. And that's basically all for eliminations.